Hi, everybody. We'll continue into section 5.2 today. Our learning targets are to find coordinates on the unit circle, to identify even or odd trig functions. We talked about even and odd functions in other senses. This time it'll refer to trig functions. Define and use fundamental Pythagorean and trig identities. We will find 5 other trig functions given one value and the quadrant location. And finally, we will write trig expressions in terms of other trig expressions. So let's start with this diagram right here. So we have a picture of the unit circle, and we're going to talk about the trigonometric functions, and you have defined those in previous courses before. Remember that when we'll start first with the sine of our angle, and in this case, I guess I'll just call it, let's call it theta for lack of anything too much more creative than that. Now remember that we are on the unit circle, so any triangle that I draw in this capacity where the point is on the unit circle, that means that we have a hypotenuse for a right triangle. The hypotenuse is of length 1. So if we look at the sine of theta, you should remember that is the opposite over the hypotenuse. And in this case, it looks like y over 1 because the side opposite has length y and the hypotenuse 1. So I'm going to write opposite over hypotenuse. So if you can remember what ratio the sine is. So in other words, on the unit circle, if we have a point on the terminal side of an angle theta measured in standard position, then its y coordinate is going to be given by the sine of theta. Or another way to put it is the sine of that angle theta is its y coordinate. If we look at cosine of theta, remember that's adjacent over hypotenuse, so that's going to give us x over 1, or simply that the cosine of theta is equal to x. And again, this only holds true on the unit circle. This is the side adjacent, the ratio of the side adjacent to the hypotenuse. Okay, the tangent of theta is equal to y over x, opposite over adjacent. And remember, x cannot be equal to 0, or the tangent of theta would not be defined, right? Because you cannot divide by 0. So there's 3 of them. We can take their reciprocals, the cotangent of theta. That's just simply the reciprocal of the tangent of theta. So that's going to be x over y. That's adjacent over opposite. And of course, in this circumstance, y cannot have value 0, or we would not have a definition for the cotangent of theta. The reciprocal of the cosine of theta is the secant of theta. So the secant of theta is going to be 1 over x. That's the ratio of the hypotenuse to the side adjacent, and it requires x to not be 0. And finally, the cosecant of theta is the reciprocal of the sine of theta. So that's the ratio of the hypotenuse to the side opposite. And again, y cannot be 0 in this capacity. So all of these things that I've drawn a box around hold true when we are on the unit circle, and that x and y represent the coordinates of a point on the terminal side of some angle theta. Okay. And I think you may have seen that before as well, but it is helpful in other circumstances. Here's one, wants the 6 trig functions of pi over 4. And I did draw special triangles on here. These special triangles don't have hypotenuse of 1, so we have to make some adjustments. The 1, 2 square root of 3, 1, that has a pi over 6 right here, we'd have to think about it as 1/2 1 square root of 3 over 2. You can remember it whichever way you want. I have always been a 1, 2 square root of 3 person, but I always realize if I'm on the unit circle, I have to go back to this one. 1, 1 square root of 2 works if your hypotenuse is the square root of 2. If you have a 45, 45, 90, or a pi over 4, pi over 4, pi over 2, and you want the hypotenuse to be 1, then these guys, the two legs, root 2 over 2, right? So whichever way that you remember those is going to be helpful. If we look at pi over 4, and I'm going back to the unit circle again, I could think about, let me just draw. Pi over 4 would be in the first quadrant, right? And again, the hypotenuse is 1. The coordinates of this point here would be root 2 over 2, root 2 over 2. Okay, so if I want the 6 trig functions of pi over 4, if I'm on the unit circle, the sine of pi over 4 is the y coordinate, which is root 2 over 2. The cosine of pi over 4 is its x coordinate, which is also root 2 over 2. The tangent of pi over 4, remember that's opposite over adjacent. Since opposite and adjacent equal each other, that ratio is just 1. Well, that makes the cotangent pi over 4 also equal to 1 because 1 is its own reciprocal. If I want the secant of pi over 4, one thing I might want to consider doing is looking at one of these drawings of a special triangle. If I'm looking just for ratios, the secant of pi over 4 would be hypotenuse over adjacent, root 2 over 1. That's just root 2. And you'll find the same thing for the cosecant pi over 4. That is also root 2. Okay, what happens if we get into 3 pi over 4? That would be this one right here. Okay, and again, we still have a 1 on the hypotenuse. The x coordinate is negative. The y coordinate is positive. So if we wanted to write the sine of 3 pi over 4, that's the y coordinate there, and it is root 2 over 2. The cosine of 3 pi over 4, though, is negative. The x coordinate there is negative. You can see that. So I have negative root 2 over 2. The tangent, 3 pi over 4. The ratio of y over x is -1 because they both have the same absolute value, but one is positive and one is negative. So we get a -1 there. And the same with the cotangent, 3 pi over 4, we also get a -1. The secant, 3 pi over 4. This is getting a little teeny here. Reciprocal of the cosine, so it's negative, and it's going to be negative root 2. And the cosecant, 3 pi over 4, is this reciprocal of the sine of 3 pi over 4, which is positive root 2. And I'm going to put an etc. here because I'm going to let you fill in the rest, right? 5 pi over 4 would be down here, 7 pi over 4 over here. And I think you should be able to fill in the rest of those values. And again, it's nice if you can use your special triangles. I don't want you to have to look at a picture of the unit circle. You should be able to put these on here without peeking, so to speak. Okay, we're going to move on to odd and evenness here. Wow. It says the sine of -t is equal to the negative of the sine of t. And that should sound like something you've heard before. In the past, when if we had f of -t is equal to f of positive t, then f of t is an even function. And if f of -t is equal to the negative of f of t, then f of t is an odd function. So in this case, we have sine of -t is equal to the negative of the sine of t. That means the sine function is an odd function. if we look at cosine of negative t equals cosine of t, that means the cosine is even. Tangent of negative t equals negative tangent of t. That makes the tangent function an odd function. Same with the cotangent of t is odd. The secant of negative t equals the secant of t. That means the secant function is even. And the cosecant of negative t is equal to the negative of the cosecant of t. The cosecant function is odd. All right, why should you believe this? Well, let's start with sine of negative t. And let's think about that in terms of a picture. And I'll try to, I've got a slightly different marker here that hopefully. So I'm going to draw something that looks like negative t. And the coordinates on this end of this angle here are, now I remember I'm on the unit circle, right? So I'm still, this is still the unit circle, 0, 1. I'll just kind of put some points on here to make sure we don't forget where we are. This is 0, negative 1, and so on. All right, so I know that the coordinates on this terminal side are of the form cosine negative t, comma, sine of negative t. If you remember on that first slide when we were on the unit circle, the coordinates of any point on the terminal side of some angle t on the unit circle are, the x coordinate is the cosine of that angle and the y coordinate is the cosine of that angle, cosine comma sine. Okay, so what about positive t? So if I put positive t, I wish I had, I've got a green one here. I don't know if it's going to show up green or not. I'll try. Let's suppose that's t. And again, this t is positive. So it has the same magnitude as the other one. So its coordinates here are cosine t, comma, sine t. Okay, and you can see that cosine of negative t and cosine of t are the same, right? You can see that it's just a reflection across the x-axis there. So the cosine of negative t equals the cosine of t validates that one. But notice the y coordinates are opposites of each other, right? Because this one is below the x-axis, this one is above. So that means that the sine of negative t, that y coordinate there is the opposite of that y coordinate. So we have confirmed those two. Okay. The others I think are left possibly as proof for homework problems. I could consider those, that tangent of opposite t is equal to the opposite of tangent of t. And actually I think we can address that just a little bit later on when we have to use some of our fundamental identities. But once we cover fundamental identities, if you'll recall that, that the tangent of t is equal to the sine of t divided by the cosine of t, right? So if I want to look at the tangent of opposite t, that's equal to the sine of opposite t over the cosine of opposite t. But we just confirmed that the sine of opposite t is opposite the sine of t. The cosine of opposite t is equal to the cosine of t. So I have the opposite of sine t over cosine t, and that equals opposite tangent t. So I have confirmed the tangent function is an odd function. And again, the rest of those, I think you have to address perhaps in homework problems. Let me be really clear that you do not ever write just sine or cosine or tangent without the t or the x or whatever theta, whatever operator you have. You absolutely must, or I think they call that an argument, but it has to be there. You can't just, sine all by itself doesn't mean anything. So make sure you are really, really clear about that. This is another one of those examples. I'm not going to do the entire thing, but we should have some idea. We kind of touched on this a few slides ago. I wanted to divert your attention away and then come back. And let's see if we can do this. For part A, I need negative pi over 4. that's going to be measured in the clockwise direction right there. Okay, and there's my my right triangle. If we think about a hypotenuse is 1, this is √2/2. This is -√2/2 because we're going down below the x-axis. Let's think about this. The sine of -π/4 is equal to the y-coordinate. Like, think about this as a point, √2/2, -√2/2. The sine of -π/4 is just -√2/2. The cosine -π/4 is +√2/2. That's the x-coordinate. Or if you like, think of it as y over, or the opposite over the hypotenuse. The cosine value there would be the adjacent over the hypotenuse. The tangent of -π/4, y over x, they're opposites of each other. The cotangent of opposite π/4 is also equal to -1. The secant of -π/4 is the reciprocal of the cosine, which will be +√2, and the cosecant of -π/4. It's the reciprocal of the sine value there. It's negative, so it's -√2. And again, I'm going to write et cetera here because you should be able to fill in those others as well. All right, let's do some identities. The reciprocal identities, I talked about the quotient ones just a little bit ago. The cosecant of t is 1 over the sine of t, and the secant of t is 1 over the cosine of t. So you need to know which ones are reciprocals of which. It's common for people to mix up thinking the secant of t is the reciprocal of the sine of t, and that's not true. So make sure you have those straight. I think they do want to say that because they both start with letter S, and cosine and cosecant both start with C, but that's not a good way to try to remember that because it's incorrect. So anyway, you have to get those two right. The cotangent of t is the reciprocal of the tangent of t. Other identities, tangent of t is equal to sine of t over cosine of t, and cotangent t is equal to cosine t over sine of t. And I believe you have seen those before. Pythagorean identities, there are actually 3 of them. This is the one that most people remember, that the square of the sine of t plus the square of the cosine of t is equal to 1. And for clarity, sine squared of t means sine of t, that quantity squared. Or in other words, it equals the sine of t times the sine of t. So when you use a calculator, your calculator doesn't understand. If you hit the sine button and then the x squared button, it doesn't know what to do. So you'd have to enter it in this form, or perhaps this form. So that's just for clarity, and I would hope that you all know that. But this is the first of 3 Pythagorean identities, and it's easy to derive the other 2. Starting with this one, we know sine squared t plus cosine squared t is equal to 1. If I divide both sides of this by cosine squared t, I end up sine squared t over cosine squared t is tangent squared t, then plus 1, and 1 over cosine squared t is secant squared t. So there's one of the other Pythagorean identities. And I'll derive the third one, again, starting with sine squared t plus cosine squared t is equal to 1. This time I'm going to divide everybody by sine squared t. And I get 1 plus cotangent squared t is equal to cosecant squared t. And to be perfectly honest, the only one of those I ever remember is this one right here. Sine squared t plus cosine squared t is equal to 1, and I derive the other 2 whenever I need them, so that I don't have to plug my head up with too many things to try to remember. All right, if sine of t is equal to square root of 21 over 5 and t is in quadrant number 2, find the other trig functions of t. Okay, so we know that sine squared t plus cosine squared t is equal to 1. And I know the sine of t is root 21 over 5. And that would, when I square that, I get 21/25 plus cosine squared t is equal to 1. So that means cosine squared t is equal to 4/25, and cosine t is plus or minus 2/5. Since t is in quadrant number 2, if you looked at a quick sketch, and we know we're in the second quadrant here, there's my picture of t. Okay, the cosine of t is the x value if you happen to be on the unit circle, so you should expect a negative cosine value. We need cosine t less than 0. So cosine t is equal to -2/5. A faster way to work on this problem would be this. The sine of t is the ratio of the opposite side to the hypotenuse. So if I instead think of my hypotenuse as 5, and this is the square root of 21, then I can figure out the -2/5 by using Pythagorean identity. I now know what the cosine of t is. Now it's not too hard to find the tangent of t. You could think of it as the sine of t divided by the cosine of t if you wanted to. The sine of t divided by the, but you could also think about it as opposite over adjacent if you wanted to. But you could think about it as root 21 over 5. That's the sine of t divided by -2/5. And you end up with negative root 21 over 2. And I should put this as a 2, a -2 here. Because if I did, 25 minus 21 would give me 4. And I need a negative there because I'm to the left of the y-axis. So here's x and here's y. With that kind of a picture, then the cotangent of t is just equal to -2 square root of 21 over 21, the reciprocal of the tangent t. The secant of t is -2/5, the reciprocal of the cosine, and the cosecant of t is equal to 5 square root of 21 over 21. Okay, and again, you can either use the Pythagorean identities to get there, or if you draw a picture like this, sometimes that's my preferred way. I think it's a little bit faster. All right, here's another problem, right? Sine of t in terms of cosine of t if t is in quadrant number 4. Okay, so my t is over here someplace. There's my t. And I expect sine of t to be less than 0 in quadrant number 4. Okay, I know that sine of t plus cosine t is equal to 1, and that makes, oops, squared, sorry. So sine squared t is equal to 1 minus cosine squared t, and sine of t is equal to plus or minus the square root of 1 minus cosine squared t. And we expect it to be less than 0 in quadrant 4. So in this case, sine of t is equal to the negative square root of 1 minus cosine squared t. In other words, this is writing sine of t in terms of cosine of t. In other words, if we knew the cosine of t, we could find the sine of t easily enough. All right, one more example and then we're done. Write tangent t in terms of sine of t if t is in quadrant number 3. So that means t is over here. And we expect sine of t to be less than 0. We expect cosine of t to be less than 0. We expect tangent of t to be positive. Okay, so let's sort this out. I know that tangent t is equal to the sine of t over the cosine of t. And we were supposed to write this in terms of sine of t. The cosine of t, we just found out a little bit ago. I know that sine squared t plus cosine squared t is equal to 1. So cosine squared t is equal to 1 minus sine squared t. And cosine t is plus or minus the square root of 1 minus sine squared t. Okay. I already know that the sine of t is negative, so I need the cosine of t to also be negative. And there is my tangent of t in terms of sine of t, right? Now remember, the sine of t in this quadrant number 3 is already negative, so negative divided by negative does give me the positive that I want. So this is kind of a think problem. You have to sort that out. Why do I need that negative sign there? All right, here's homework from this section. This is again in section 5.2. I think that you've seen a lot of this material before, but again, it may be a little bit shaky and some of you may know it better than others. So best wishes, and we'll talk again soon.